Before MLOps, the path from a data scientist's laptop to a live application was a broken, frustrating process. We call this the Great Divide. On one side, data scientists created brilliant models in isolated notebooks. On the other, an operations team struggled to keep applications running. The journey between them was a manual, error-prone handover that led to the infamous phrase, "But it worked on my machine," causing delays and failures. So, what exactly is MLOps? It's a culture and a set of practices that aims to unify the development of machine learning systems, ML, with their operation and deployment, Ops. It's not just a tool, but a philosophy. To understand it better, let's break down its name. It's a fusion of three critical disciplines: machine learning, development, and operations. To visualize the MLOps solution, think of it as building a sophisticated, automated factory for your machine learning models. Instead of manually carrying parts between islands, MLOps constructs a high-tech assembly line. This assembly line automates everything from processing raw data to building, testing, deploying, and monitoring models, ensuring a fast, reliable, and repeatable process. This AI factory is the core concept we'll build throughout this masterclass. Now that we understand the what and why, let's look at the blueprint for our AI factory, the MLOps lifecycle. This is a continuous, iterative process, not a linear one. It guides a model from a simple idea to a constantly improving production asset. We'll use this lifecycle as our roadmap, and in the upcoming scenes, we'll dive deep into each stage, starting with the foundation of all machine learning, the data itself. Our journey begins with the first stage, data engineering. This is where we source, prepare, and manage our data. It involves ingesting raw data from various sources, validating its quality to catch errors early, and transforming it into a clean, usable format. Think of this as sourcing high-quality raw materials for our factory. Without good data, even the best model will fail. Within data engineering, a critical MLOps practice is data versioning. Just like we version control our code, we must version control our datasets. This means taking a snapshot of the exact data used to train a specific model version. This practice is the bedrock of reproducibility. If a model behaves unexpectedly, we can trace it back to the exact data it was trained on, which is crucial for debugging and auditing. As MLOps has matured, a specialized tool has become essential: the feature store. This is a centralized repository that manages and serves curated data features for both model training and real-time inference. Instead of each data scientist creating their own features in isolation, they are standardized and stored here. This provides a single source of truth for features across the organization. The most critical problem a feature store solves is training serving skew. This silent killer of models occurs when the features used for training are calculated differently than the features used for live predictions. For example, a feature calculated in a batch process for training might differ from one calculated in real time for serving. The feature store ensures the exact same feature logic is used in both cases, eliminating this common source of failure. With our data prepared and versioned, we move to the second stage, model development. This is the creative phase where data scientists explore data, engineer features, and train various models. In an MLOps context, this is not a free-form process. A core practice is rigorous experiment tracking. Every experiment, including the code version, data version, parameters, and resulting metrics, is logged automatically. This creates an auditable and reproducible history of all modeling attempts. Once a promising model is identified through experimentation, we need to prepare it for the automated pipeline. This involves packaging the model and all its dependencies, like specific library versions, into a standardized, portable format. The most common method is containerization, using tools like Docker. This creates a self-contained box that can run consistently in any environment, from a developer's laptop to a production server, solving the "it worked on my machine" problem once and for all. Now we arrive at the engine room of our AI factory, the automated CI/CD/CT pipeline. This is where we connect all the pieces we've discussed. This pipeline automates the building, testing, and deployment of our packaged model. It is triggered automatically, for instance, when a data scientist commits new code. Let's break down the three components of this pipeline: continuous integration, continuous delivery, and continuous training. The first step in our pipeline is continuous integration, or CI. In software engineering, CI focuses on testing code. In MLOps, CI is much broader. It includes not just code unit tests, but also automated tests for data validation, model validation against a baseline, and even checks for fairness and bias. A model only proceeds to the next stage if it passes this comprehensive suite of tests. After a model passes all CI checks, continuous delivery, or CD, takes over. This stage automates the release process. The packaged model is first pushed to a model registry, which is a central version-controlled repository for all production-ready model artifacts. From the registry, the CD system can then automatically deploy the model to a staging environment for final testing and, ultimately, to production. Within continuous delivery, mature MLOps practices use sophisticated deployment strategies to minimize risk. Instead of a big bang release, we can use strategies like a canary release, where the new model is initially exposed to a small fraction of user traffic. We monitor its performance closely, and if it performs well, we gradually roll it out to everyone. This allows us to catch problems with minimal impact on users. The final piece of our pipeline is continuous training, or CT, a concept largely unique to MLOps. CT is the automated process of retraining and redeploying models in production. This isn't about a data scientist manually kicking off a new training job. Instead, the system is designed to automatically trigger retraining based on a schedule, the availability of significant new data, or, as we'll see next, a decline in the live model's performance. With our model deployed, the journey isn't over. In fact, it's just beginning. We now enter the crucial, ongoing stage of monitoring. Crucially, we must monitor more than just system health like CPU usage or latency. We must perform ML-specific monitoring to answer key questions. Is the model's predictive accuracy still high? And more importantly, has the real-world data it's seeing started to differ from the data it was trained on? One of the most critical silent failures we monitor for is data drift. This occurs when the statistical properties of the input data in production change over time, becoming different from the training data. For example, a fraud detection model trained before a global pandemic might see very different user spending patterns after. Data drift is a major warning sign that your model's view of the world is now outdated. Another subtle issue is concept drift. Here, the input data statistics might stay the same, but the relationship between the inputs and the output changes. For instance, in a housing price model, the concept of a desirable feature might change over time, like a home office becoming much more valuable. The features themselves haven't drifted, but their meaning has. This is harder to detect, but equally damaging to model performance. This brings us full circle, closing the MLOps loop. When our monitoring system detects significant data drift, concept drift, or performance degradation, it doesn't just send an email to a human. Instead, it acts as the trigger for our automated feedback loop. This alert automatically initiates the continuous training (CT) pipeline, which pulls in the latest production data, retrains, validates, and redeploys the model. This is how MLOps creates truly adaptive AI systems. Organizations don't achieve this level of automation overnight. MLOps adoption is a journey through different maturity levels. It typically starts at level 0, a completely manual process full of pain points. Level 1 introduces automation for the ML pipeline but keeps deployment manual. The ultimate goal is level 2, which achieves full CI/CD automation for rapid, reliable updates, creating a system that can be improved and redeployed with high velocity. Finally, it's crucial to remember that MLOps is not just about tools and automation, it's about people and collaboration. A successful MLOps culture breaks down the silos between data scientists, ML engineers, and DevOps operations teams. These roles work together in cross-functional teams, each bringing their unique expertise to build and maintain the AI factory. Clear communication and shared ownership are just as important as the CI/CD pipeline. In summary, MLOps transforms machine learning from a research-oriented manual craft into a disciplined, automated, and scalable engineering practice. By building this AI factory, organizations can deploy models faster, manage them more reliably, mitigate risks, and continuously adapt to a changing world. It is the essential bridge that carries a promising model from a data scientist's notebook to creating real, sustained value in the real world.